Good day everyone. Today's topic is on probability and finding the area under the normal curve. In this tutorial, we will focus only on the principles and ideas necessary to lay the groundwork for inferential statistics. We can accomplish this by quickly tying the concepts of probability to what we already know about normal distributions and z-scores. Now, what is probability? Probability is how likely something is to happen. Whenever we're unsure about the outcome of an event, we can talk about the probabilities of certain outcomes, how likely they are. The chance of raining today is an example of an event. Likewise, rolling a 6-sided die is an example in probability. We could roll a die and see if it is a 5 or not. The chance of getting a 5 is called probability. The analysis of events governed by probability is called statistics. In mathematical form or equation, the probability of an event is equal to the number of outcomes that satisfy a criterion, divided by the total number of possible outcomes. Suppose we ask ourselves about the probability of getting number 5 when tossing a die. The solution is this. A die has 6 sides, and one of those sides is number 5. So, the number of outcomes that will satisfy our criteria is 1. Meanwhile, the total number of possible outcomes is 6, since the die has 6 sides. Now, let's substitute 1 and 6 to the formula. So, we have 1 divided by 6. Therefore, the probability of getting a number 5 is 1 over 6, or 16.67%. Now, let's find the probability of getting an even number if we toss a die. The solution is this. There are 3 even numbers on a die, namely 2, 4, and 6. Hence, the number of outcomes that will satisfy our criteria is 3. Further, that has 6 sides, so the total number of possible outcomes is 6. Now, let's substitute 3 and 6 to the formula. So, we have 3 divided by 6. Therefore, the probability of getting a number 5 is 3 over 6, or 1/2, or 50%. The normal distribution is the key to how probability works for our purposes. Recall that a pie chart represents how frequently a category was observed. In this case, all slices of the pie chart add up to 100%, or 1. The probability of taking a specific value is exactly equal to the size of that category slice in the pie chart. As an example, the pie chart in the current slide represents the favorite sports of 100 people as a village. The probability of meeting a person whose favorite sport is baseball is 36%. Likewise, the probability of meeting a person whose favorite sport is football is 25%. In this example, the probability is equal to the proportion of the chart taken up by that group of people with the same favorite sport. Next, let's talk about the probability in normal distributions. Recall that the normal distribution has an area under its curve that is equal to 1. The normal distribution can be split into sections by drawing a line through it that corresponds to a given z-score. Because of this, we can interpret areas under the normal curve as probabilities that correspond to z-scores. First, let's look back at the area between z equals minus 1.00 and z equals 1.00, as shown in the figure. You learned in the previous chapter that this region contains 68% of the area under the curve. Thus, if we randomly chose a z-score from all possible z-scores, there is a 68% chance that it will be between z equals -1.00 and z equals 1.00 because those are the z-scores that satisfy our criteria. Just like in a pie chart, we can also draw a line through the normal distribution to split it into sections by drawing lines through it. As shown in the figure, a line is drawn through at z equals 1.25. As you can see, the line creates two sections of the distribution. The smaller section is called the tail, and the larger section is called the body. Differentiating between the body and the tail in terms of their relative sizes is all that matters. The standard normal distribution table presents the values for the area under the curve, starting from the center to the positive side. In other words, it started from z equals 0 to z equals 3.00 and beyond. Furthermore, we can use the table for the areas under the normal curve from z equals 0.00 to the negative side of the graph, by setting aside the negative sign. Please note that the table shown on this slide is just a portion of the whole standard normal distribution table. Now, let's find the area to the left of z equals 1.25. As shown in the figure, this area is the portion of the graph in the color orange. In this case, we need to separate the second decimal place of the given z-score. So, we have 1.2 and 0.05. Looking at the standard normal distribution table, let us find the number 1.2 on the first column of the table. Meanwhile, let us find the number 0.05 on the first row of the table. After doing so, let us find the four decimal numbers at the intersection of 1.2 and 0.05. As you can see on the slide, the intersection is 0.3944 or 39.44%. However, the area from 0.00 to the negative side is not yet included. Recall that half the area under the normal curve is 50%. So, the total area on the left side of z is 39.44%, plus 50%, is equal to 89.44%. On this slide, you can see the illustration of the area to the left side of z equals 1.24. Now, let's have example number 2. Find the area between z equals 1.32 and z equals 2.00. To start solving this problem, draw a normal curve and plot the given z-scores. After plotting the z-scores, put a color or shade the area under the normal curve between the given z-scores, as shown in the current slide. This time, let us assign letters for labeling the areas under the normal curve. Let capital P be the area bounded by 1.32 and 2.00. Let X be the area from 0 to 2.00, and let Y be the area from 0 to 1.32. In this example, the area represented by capital letter P is the one we are required to find. Meanwhile, the areas represented by X and Y can be determined in the normal distribution table. Before we find the area under the normal distribution, we need to split the z-score into two components. The first component is the whole number up to the first decimal place. The second component is the remaining number on the second decimal place. Let's start with z equals 2.00. Let's split it into 2.0 and 0.00. As we can see in the illustration, the intersection of 2.0 and 0.00 on the normal distribution table is 0.4772. The number on the intersection tells us that the area from 0 to 2.00 is 47.72%. Hence, x is equal to 47.72%. Now let's have z equals 1.32. Let's split it into 1.3 and 0.02. As we can see in the illustration, the intersection of 1.3 and 0.02 on the normal distribution table is 0.4066. The number on the intersection tells us that the area from 0 to 1.32 is 40.66%. Hence, y is equal to 40.66%. Now let us substitute the value of x and y in the equation we formed earlier. The equation is p is equal to x minus y. So, p is equal to 47.72% minus 40.66%. And the difference is 7.06%. Therefore, the area bounded by 1.32 and 2.00 is equal to 7.06%. Now let's have example number 3. In this example, let us apply the area under the normal distribution to real-life situations involving probability. Let's read the problem. An entrance examination is to be conducted to 120 incoming first-year college students at a particular community college. Based on records, the average score of previous takers is 85, with a standard deviation of 10, and assumed to be normally distributed. The things we are asked in this problem are the following. The first is the proportion of the incoming college freshmen who are expected to score above 95. Second, the proportion of incoming first-year college students who are expected to score below 80. And the third is the number of incoming first-year college students who are expected to score between 80 and 95%. As stated in the problem, the population mean is 85, and the population standard deviation is 10. The numbers 85 and 10 are considered as population parameters, as they came from the previous records. Now let's solve letter A, which requires us to find the proportion of incoming first-year college students who are expected to score above 95. Step 1. Convert the 95 to z-score. As shown on the current slide, we have z equals 95 minus 85 all over 10. When we simplify, the result is 1. In step 2, we are going to plot the z-score on the normal curve, and shade the area indicated in the problem. In this case, it is the area above 1.00. As we can see in the illustration, half of the area under the normal curve is 50%. Meanwhile, x represents the area from 0 to 1.00, and p represents the shaded area. Since capital P is the required proportion, we have the equation P equals 50% minus x. The value of x can be found in the normal distribution table. Now let's find the area represented x. Since x is the area from 0 to 1.00, let's split 1.00 into 1.0 and 0.00. As shown in the current slide, the intersection is 0.3413 or 34.13%. Hence, x is 34.13%. At this stage of solving the problem, let us substitute the value of x in the equation we formed earlier. Since we formed the equation P is equal to 50% minus x, and the value of x is 34.13%, we have P equals to 50% minus 34.13%. Then find the difference. The result is 15.87%. Therefore, the proportion of students who are expected to get a score above 95 is 15.87%. of the number of incoming first-year college students at a particular community college. Now let's have letter B. We are asked to find the proportion of students who are expected to score below 80. Step 1 is to convert 80 to z-score. When we substitute the values on the formula and simplify it, the result is minus 0.50. This time, draw a normal curve. Plot 0.50 on the graph. Then shade the area below minus 0.50. Now, label the parts of the graph carefully. P is the required area, or the proportion of students who are expected to score below 80. X is the area from 0 to minus 0.50. Based on the illustration, we form the equation to solve for P. Hence, we have P equals to 50% minus the value of X. Now, let's find the value of X, or the area from 0 to minus 0.05. Since the table represents the positive side of the normal distribution, let us disregard the negative sign of minus 0.50. The negative sign only tells us that the z-score is on the negative side of the normal distribution. Since the normal distribution is symmetrical, we can use the positive side to find the areas on the negative side. As you can see on the current slide, the area from 0 to 0.00 is 0.1915, or 19.15%. Hence X is 19.15%. At this stage, let's substitute the value of X in the equation. So, we have P equals to 50% minus 19.15%. Simplifying, the result is 30.85%. So, the value of P is 30.85%. Therefore, the proportion of students who are expected to get a score below 80 is 30.85% of the number of incoming first-year college students at a particular community college. Now, let's solve letter C. We are asked to find the number of students who are expected to score between 80 and 95. As stated, it is the number of students, not the proportion. First, let's convert 80 and 95 to standard scores. As shown in the current slide, score 80 is converted to z equals 0.50. Likewise, score 95 is converted to 1.00. Now, let us draw a normal curve. Plot minus 0.50 and 1.00. Then, shade the area between them. Likewise, label the parts correctly, and assign letters to represent the areas. As shown on the current slide, X is the area from 0 to minus 0.05, and Y is the area from 0 to 1.00. Meanwhile, P is the area between minus 0.50 and 1.00. Based on the illustration, the appropriate equation to solve for P is P equals X plus Y. Now use the normal distribution table to find the area from 0 to minus 0.50. As shown in the illustration, the area is 0.1915, or 19.15%. Hence, X is equal to 19.15%. Now let's find the area from 0 to 1.00. As shown, the area is 0.3413, or 34.13%. So, Y is equal to 34.13%. At this stage, Let us substitute the values of x and y in the equation we formed based on the graph. Since we have p equals to x plus y, then p is equal to 19.15% plus 34.13%. So, we have p equals to 53.28%. Therefore, the proportion of students who are expected to get a score between 80 and 95 is 53.28%. However, what was asked is the number of students. So multiply 53.38% to the number of incoming first-year college students, which is 120. So, we have 120 times 0.5328. The result is 63.936. Since the result refers to the number of students, we rounded it off to the nearest whole number. Therefore, the final answer is 64 students. Thank you for watching. Have a nice day.